Hey, hello class. Let me work on another solution. I got a good one here. It's from our chapter 20, so our thermodynamics in number 16. And it simply says this, that you have steam at 100 degrees Celsius, different pen, at 100 degrees Celsius. And you are going to add it to ice at 0 degrees Celsius. It says then, find the amount of ice that melted and the final temperature of the mass and the steam. I'm sorry, find the amount of ice melted and the final temperature when the mass of steam is 10 grams and the mass of ice is 50 grams. All right, well, let me use this as a moment to kind of review here, because this whole chapter is centered around this whole idea that there is energy, and this heat energy Q comes in two calculations. And we can have energy because the molecules slow down or speed up. And so that is a change in temperature. So there's the MC delta T. But we can also say that there is an energy when the bonds break. And so if we were going from, say, a solid and we partially break the bond so we become a liquid, we call that the latent heat of fusion. I'll put a comma because we could also then go from the liquid and completely break the bonds and go into then a gas or a steam in the case of water. And so we'd call it the latent heat of vaporization. And so when we are changing the, I don't want to say temperature, when we are adding energy, the energy can go into either breaking the bonds, and so as it changes phases, there's a breaking of the bonds, or the energy can go into changing the kinetic motion of it, and so that's a temperature. So we need to consider these, and that's what makes this problem kind of hard, because there is not a one continuous equation. This is what in a math class you would call a piecewise set of equations, and that's what's going to make this problem a little bit challenging, because here's the question. Certainly the steam would start to cool and become a liquid, and of course it would become a liquid at 100 degrees, and of course as it and I shouldn't use the word cool. I should have said the steam is going to give off its energy and change from a gas, that is a steam, into a liquid. Okay? And while it does that, it gives its energy to the solid ice, and so the solid ice is going to become a liquid. And here's kind of this question that, okay, which is going to happen first? Does all the steam become a liquid, and so now that begins to cool down? Or does all the ice become a liquid and it starts to warm up? So how you want to do this, there is no one way, but I like to just look at, I'll call it the accounting method, and say, okay, well, how much energy would have to be given off by this hot steam in order to become a liquid. Now, it'd still be a liquid at 100 degrees. But let me use this calculation here. So I'm going to say Q equals, and so I'll start with the mass. So the mass is 10 grams. And then I'll look up the latent heat of vaporization. And so we see that it's about 540 calories per gram. And that would say that 5,400 calories would then be released by this hot steam in order to make all the 10 grams of steam turn into now it would be a hot liquid. And then we got more to talk about at that point. But let me also go the other direction here. let me take the 50 grams, okay, so the M, the mass of the ice, and say, all right, how much energy would need to go into the ice in order to melt all that ice? All right, so we look up the latent heat of fusion of water, and we see it's near 80 calories per gram. And so 5 times 8 is a 40, and then 2 more zeros. Now there is our good starting point. Notice then that as this begins to turn from a gas into a liquid, it will be melting the ice. And to melt all the ice only takes 4,000. So this right here, being a bigger number, means that only a certain amount, not the whole 10 grams. You might even be curious how much it does, and so you might do something like this. You might say, how much mass, knowing that each gram gives off 540 calories per gram, would equal the 4,000, because we know that 4,000 is going to go to melt the ice. And I'm not sure you even have to do this calculation to complete the problem, but I'm kind of curious. And I'm hoping it will help you kind of understand what's going on here. So if I take 4,000 and divide it by 540, this would tell me that 7 point, I'll just call it 41 grams, would turn from a gas into a liquid. Now, of course, we still have a liquid at 100 degrees, and we still have, it looks like, a little bit, whatever the difference between 10 and this is, so that'd be 2.6. We still have 2.6 grams still left as steam, okay? All right, so that kind of gives us an idea what's going to happen. And like I said, that's just an important part, because I didn't know what would happen next. I didn't know if all of this ice would melt and then start to warm up, or if all of this steam would condense and then go cooling down. But now I do know. Now I know that what's going to happen first is all the ice is going to melt, okay? And it's going to start warming up. Now, of course, as it warms up, more and more of this steam is going to condense. In fact, here's the next question in all of this. As this other 2.6 grams of steam is condensing, would it be enough energy to warm up this, which was ice, but now is liquid, water? Would it be enough to warm it up to the 100 degrees? And thereby you still maybe have a little bit of steam left? Or does the water from the ice warm up to maybe, say, 60 degrees or something? And then all the steam now has turned into a liquid. And so now the two liquids are going to merge. That is, the hot liquid is going to cool down and the cold liquid is going to warm up. Don't really know, but I'm going to play the same little accounting game. I'm going to just ask this question. How much energy would it take this 50 grams of what would be now water and warm it up to 100 degrees? So let me try that calculation. So Q equals MC delta T. All right, so the mass is 50 grams. The specific heat of water is 1 calorie per gram per each degree. And the change in temperature would be 100 if it was going to, warm up the full 100. And so this would be 50 times 100, that's 5,000. And maybe I should put degrees Celsius so that grams and degrees Celsius cancel off, and I got 5,000 calories. Okay, so wait a minute. coming back to my earlier calculation, if the first 4,000 was needed to melt the ice, then I'm going to see here that there's no way the remaining 2.6 grams is going to be able to give off 5,000 more. In fact, I can even see there's only 1,400 more left to give off. Okay. So that does tell me then that there is going to be a warming up of this water here while the next 1,400 calories goes into this water, making this water then at 100 degrees, and then this warming up to some value, which maybe I'll calculate that. All right, well, let me put a page 1 on this one, okay? Because over here on page 2, then, I'm going to kind of come back to these numbers and say, okay, let's see what my numbers just told me. My numbers told me that some of the steam will condense. In fact, 7.41 grams will condense, giving off 4,000 calories. Those 4,000 calories will go into the ice and melt it. So the steam, there's still going to be this 2.6 grams left, which would correspond to 1,400, right, the difference between these, 1,400 more calories. And that's going to be warming up then this water, which was once ice. So let me do this. Q equals MC delta T. So the Q is these 1,400 calories. And that 1,400 calories, again, comes from the rest of the 2.6 grams of steam condensing. And it goes to warm up this, which is now water. Started with ice, but is now water. All right, so I would have this 50 grams with a specific heat of 1 calorie per gram per degree Celsius. And that would be then the delta T. So this would give me an idea of how much that 0 degree water is going to warm up. And so 1,400 divided by the 50, and I guess technically divided by the 1. Calories will cancel with calories, gram with gram, and we're going to be left with degrees Celsius. And what do we get? 28. So again, kind of following this. So this tells me that this is going to warm up to about 28 degrees Celsius when finally all the steam has condensed into water at 100 degrees. And so now the last process is the water is going to cool down, the water that came from the steam. And the water that came from the ice is going to warm up, and they're going to meet someplace between them. Now, we have a lot more of the colder water, 50 grams, than we do of the warm water. So it's not going to meet in the middle. In fact, it's going to be like a 5-to-1 ratio. So if you took the difference between them divided by 6, and then take that 1 part of 6, that's what this is going to come up to. All right, but we won't do it in terms of proportions. Let's just actually calculate it out. Okay, so now I'm going to say this, that the energy coming from the hot one, and I'll do a conservation of energy way, the energy going into the cold one would be 0. And remember our sign convention, And not all books use the same sign convention, but heat energy going in is a positive. So the Q going in here is a positive going into the cold water, and coming out is a negative. And so what comes out of the hot water goes into the cold water. So we got a negative and a positive, which is going to come out to be 0. So I'll just put MC delta T and just remind myself this is for the hot water. And then I'll put an MC delta T and put a little cold under here and say this is the cold water. Now what's nice here is they're both water, so they both have the same C. We can factor that out and divide it by the 0, and that'll go away. And here is our, 5-to-1 ratio, because the hot water has a mass of 10 grams. And so the change in temperature is going to be the final minus the initial. So we are going to cool down to some number. We're at 100 degrees for the hot water. That's the 10 grams that converted from steam into hot water. And then this is the 50 grams. And it's going to have some final temperature minus its starting temperature, which is 0. So you can hopefully see here that this would be a 50 final temperature and a 10 final temperature to make a 60 times the final temperature. And then this right here would make 1,000 with a negative sign. So when I move it to the other side, it's plus 1,000. And so the final temperature is 1,000 divided by 60. And it looks like we are... Oh, my bad. Totally bad. Sorry. Didn't... glad I saw that as I looked at the answer. The initial temperature is not 0. We just said that. We just said that once the rest of the steam condenses, it has warmed up the cold water to 28. So this is supposed to be a 28. Okay. So, sorry about that. Okay, let me try that again. I will still say that the 10 and the 50 make the 60 times the final temperature. And maybe I'll just move this to the other side, so that's the 1,000, and then over here this would be then the plus the 50 times the 28. So this is 2,400, and so the 2,400 divided by the 60 gives me a temperature of 40. So the final temperature here is 40, at least for that part of the answer here. Because the other part of this, part B, says go ahead and repeat all of this when the mass of the steam is 1 gram and the mass of the ice is still 50 grams. All right, so we've got a lot less steam. 10 times less. So let's come back to our conversation that we had before. Back here, and we said, okay, well, how much energy would be given off by that steam as it condensed? And so maybe switching a color here and just saying, well, let me not do the whole calculation again here, but let me just change this to 1 gram. It's 10 times smaller, so that's going to be 540. Now, 540 calories is way less now than the 4,000 that was needed and would still be needed to melt all the ice. So I would say then that in this case, what would happen first is all the steam would become a liquid. And only a small fraction of the ice would melt. And we could even calculate that, but I'm beginning to think that it's such a small fraction that once we get to this 1 gram of liquid water, it's probably even going to cool all the way down and get to 0 degrees before you even get a chance to melt all this ice. So kind of like we were talking here, let's talk about that. How much energy would that be for it to cool all the way down? And so that was this calculation. And so let me change that to a 1. And so 1 times 100, of course, is only 100 calories. So what I'm saying here is for 1 gram of steam to completely condense and then completely cool down to 0 degrees would only be a total of 640 calories. And again, we said it's going to take 4,000 in order to melt all the ice. So there we go. We don't get a chance to melt all the ice. We'll have kind of a mixture of water and ice. The amount of water, I guess, would be the 1 gram from the steam cooling down, plus however much actually melted. I guess we could figure out how much melted by putting in the fact that the total energy given to the ice from the condensing steam and then the cooling down of that would then be this latent heat. Let's see, what's 80? And so, if again, not really part of this question, but it might be nice to kind of see what it is. It looks like the mass is 8 grams. So it looks like in the process of this 1 gram of steam condensing and cool all the way down, it will melt 8 grams of the ice. So we will then ultimately have 9 grams of water sitting there. And let's see, still a lot of ice because 50 minus the 8 that melted is 42. So we'd have 42 grams still of ice and then 9 grams of liquid water that had cooled down or melted to 0 degrees. Anyway, so the answer to B is actually much, much easier. It's just the final temperature would be 0 degrees Celsius. If you're going to have a liquid and solid at the same time, you got to be at 0 degrees. So this one, again, got to be careful with it because it's one of these, what in a math class you'd call, you have to piecemeal it. You got to, because which formula to use kind of depends on what's happening here. And so we don't have this one formula that can be used to calculate the energy from ice all the way up to steam. We've got to decide on the piecemeal of it. And to decide that, we have to know which one, melted first. And anyway, so that's why you got to go through this process here of kind of thinking it through. So it's a good problem where, if you've fallen into the trap of just blindly plugging and chugging, you're going to run into troubles. This one, you got to follow the numbers. You got to read the math as you go along. All right, hope that helped.